It is 8:13 a.m. on August 17, 2009, inside Russia's Sayano Shushenskaya hydroelectric power station. Workers going about their standard morning routine suddenly witness the impossible. A solid steel spinning rotor weighing over 920 tons begins to rise up out of the floor entirely on its own. Before anyone can comprehend the sight or reach the emergency controls, a volcanic eruption of highly pressurized water blasts through the thick concrete. Just listen to the sheer destructive power of a high-pressure breach. The ensuing flood obliterated the machine hall in a matter of seconds. 75 people were killed, 9 out of 10 massive generating units were utterly destroyed, and 6,400 megawatts of electricity vanished instantly from the grid. Yet the most terrifying detail of this catastrophe is what did not happen. The enormous dam did not collapse, and there was no earthquake to rattle the foundation. The complete annihilation of Russia's largest power plant began in absolute secret, triggered by a microscopic flaw hiding deep inside the machine itself. To understand how a microscopic defect could cripple an entire region, you first have to grasp the sheer scale of Sayano Shushenskaya. Deep in the remote wilderness of Siberia, the Yenisei River carves a path through the Sayan Mountains. Blocking this massive waterway is a curved arch-gravity dam standing 242 meters tall. That is nearly the height of a 70-story skyscraper, constructed from over 9 million cubic meters of solid concrete. Its crest stretches over 1,000 meters across the river valley. The structure was engineered to hold back a sprawling reservoir containing over 30 cubic kilometers of water. When the spillways open to relieve the intense pressure, the raw kinetic energy is staggering. Just listen to the immense roar of the unleashed Siberian River. Tucked away at the base of this colossal wall was the machine hall. It housed 10 titanic hydro-turbine generating units. When operating at peak efficiency, these machines produced a combined output of 6,400 megawatts. This made Sayano Shushenskaya the undisputed largest hydroelectric power station in Russia and a crown jewel of global engineering. However, this facility was not primarily designed to light up residential neighborhoods or nearby cities. It was built specifically as the beating heart of the Soviet and later Russian industrial machine. The Siberian territory is dominated by massive aluminium smelters. Extracting pure aluminium from raw bauxite ore requires a continuous extreme supply of direct electrical current. The smelting process is so incredibly energy hungry that economists often describe exported aluminium as packaged electricity. Sayano Shushenskaya existed to feed these specific factories. Its turbines ran under constant heavy loads day and night to keep the molten metal flowing. Because of this deeply integrated relationship, the dam was an irreplaceable titan of the regional electrical grid. It supplied more than a quarter of the entire power demand for the vast Siberian territory. There were simply no secondary power stations capable of stepping in if this mega dam went offline. It carried the industrial economy on its back, meaning a sudden failure in the machine hall would instantly paralyze supply chains hundreds of miles away. Inside each of those 10 generating units, the river is forced through a massive steel pipe called a penstock. Falling from a height of over 200 meters, the water accelerates dramatically before slamming into a precisely engineered spiral casing. This structure acts like a giant snail shell, squeezing the rushing liquid and guiding it into a tight, high-speed vortex. At the very center of this whirlpool sits the turbine runner. This is a massive steel wheel fitted with intricately angled blades. As the vortex tightens, the water strikes these blades, transferring its raw kinetic energy and forcing the runner to spin at exactly 142.8 revolutions per minute. Surviving inside this machine requires withstanding extreme, fluctuating, and often chaotic forces. Every single second, over 300 cubic meters of water blast through the turbine casing. That is roughly 300 metric tons of mass tearing through the system in the blink of an eye. This relentless flow creates a violent three-dimensional assault on the machinery. The sheer weight of the descending water pushes heavily downward, while centrifugal forces push violently outward against the metal walls. At the same time, the high-pressure flow rushing underneath the spinning blades creates a massive continuous upward thrust. To contain this relentless hydromechanical violence, the entire turbine assembly is capped by an enormous heavy steel head cover. You can think of this cover as a massive lid clamped onto an industrial pressure cooker. Keeping this heavy lid sealed tightly against the upward thrust of the river relies entirely on a single ring of 80 steel studs. Each of these threaded fasteners is roughly 8 centimeters thick, secured firmly into the foundation with a heavy-duty nut. These 80 steel fasteners represent the ultimate, non-negotiable line of defense for the entire facility. Below them lies the unyielding, crushing pressure of a sprawling Siberian reservoir desperate to find an exit. Directly above them sits the dry, open floor of the machine hall where dozens of technicians and engineers work their daily shifts. There are no secondary containment domes, no backup seals, and no emergency blast shields. If those 80 specific studs stretch, crack, or shear off, the pressure boundary vanishes. There would be absolutely nothing left to stop the full force of the Yenisei River from bypassing the turbine runner entirely and erupting straight upward into the powerhouse. Unit 2 had been spinning inside the Sayano Shushenskaya dam for nearly 30 years. But the age of the heavy steel machinery was not the primary problem. The real threat was how the unit was operated and maintained. In early 2009, Unit 2 underwent a scheduled modernization. Over the decades, relentless water pressure and cavitation had slowly carved deep pits into the steel turbine blades. Technicians welded these cavities, filled to restore the smooth surfaces, but they made a critical engineering error. After adding asymmetrical amounts of new metal to the blades, they failed to properly rebalance the massive runner. It was exactly like putting a patch tyre on a highway vehicle without balancing the wheel first, only this involved a rotating mass weighing hundreds of metric tons. When Unit 2 was brought back online, the consequences of this poor maintenance became immediately obvious. The uneven weight distribution caused the entire turbine shaft to wobble. Over the next few months, bearing vibrations steadily increased as the imbalance took its toll. By the summer, the heavy shaft was shifting laterally by 0.84 millimeters. While less than a single millimeter might sound microscopic, for a machine of this sheer size spinning at 142.8 revolutions per minute, it was a massive and highly destructive amount of physical movement. Every single rotation forcefully hammered away at the internal guide bearings and surrounding structures. Making matters much worse was the fundamentally counterintuitive nature of Francis turbines. You might expect a massive hydroelectric machine to shake the most when pushed to its absolute maximum output, but these specific turbines actually run incredibly smoothly at full power. The true danger lies in an unfavourable intermediate power band. When operated at medium loads, the velocity of the water flow no longer matches the fixed angle of the spinning blades. The rushing river physically separates from the steel surfaces, creating violent pressure pulses and chaotic vortexes beneath the runner. For months, grid operators repeatedly forced Unit 2 into this exact unfavourable zone to regulate the regional power supply, drastically compounding the severe vibrations actively tearing at its foundation. To understand why this regulation was so destructive, you have to look at how grid balancing actually works. An electrical grid requires power generation to perfectly match consumer demand at every second of the day. As millions of people turn appliances on and off, power stations must constantly change their electrical output. For a hydroelectric plant, this means continuously adjusting the volume of water flowing through the penstocks, an action that inevitably forces the turbines to pass through their unstable dead zones as they transition between high and low power. This routine wear and tear escalated into a localized crisis on August 16, 2009. A fire broke out at the nearby Bratskaya hydroelectric power station, severing its vital communication and control cables. The blaze effectively knocked the entire facility out of the regional grid. To prevent a cascading blackout across Siberia, Sayano Shushenskaya was immediately ordered to take over Bratskaya's network regulation duties. The plant's automated control system designated Unit 2 as the primary regulating turbine. Overnight and into the early morning hours of August 17th, the machine's electrical output was aggressively manipulated. As the regional grid demanded more or less power, the system relentlessly chased those rapidly changing requirements. Unit 2's load rose and dropped sharply, over and over again. With every single shift in power, the software dragged Unit 2 straight through its dangerous intermediate power band. The turbine repeatedly entered its unstable hydraulic range, where rushing water physically separated from the steel blades and created chaotic pressure vortexes. Already crippled by a severely unbalanced rotor and degraded bearings, the heavy machine was subjected to violent pulsing stress, hammering its weakened internal components toward a catastrophic mechanical failure. If you want to break a metal paperclip, you do not try to pull it apart with one massive tug. Instead, you bend the wire back and forth over and over again until the internal structure degrades and snaps. This is the fundamental concept of metal fatigue. A heavy industrial component will rarely break from a single heavy load. However, if you subject that same solid metal to millions of smaller, repetitive stresses, the atomic bonds will slowly begin to slip, forming microscopic cracks that grow wider with every cycle. Inside Unit 2, this relentless bending effect was focused directly on the enormous steel studs bolting the turbine cover down to the plant foundation. These heavy fasteners were tasked with keeping the massive cover locked in place against the immense upward pressure of the river. But every time the control software dragged the turbine through its unstable zone, chaotic water vortexes violently shoved the entire assembly upward, physically stretching the steel studs. When the pressure dropped seconds later, the studs slammed back down. This continuous loading and unloading cycle was heavily amplified by the extreme vibrations radiating from the unbalanced rotor. The horrifying scale of this microscopic death was only revealed during the post-disaster investigation. When forensic engineers examined the ruined turbine pit, they recovered 49 of the heavy steel studs that had originally secured Unit 2. The laboratory results were staggering. 41 of those recovered studs showed clear evidence of extensive fatigue cracking. Even more terrifying, the cross-sectional integrity of 8 specific studs was 90% compromised long before the morning of August 17th. Only a tiny fraction of solid metal remained intact in the center of those critical bolts. The primary mechanical fasteners holding the heavy turbine against the crushing force of the water were essentially destroyed before the final crisis even began. Years of invisible fatigue had silently eaten through the solid steel. Unit 2 was a ticking time bomb, held together by virtually nothing, simply waiting for one final, unbearable push to tear itself right out of the concrete floor. At exactly 8:12 a.m., the automated turbine regulator made a routine adjustment. Sensing a minor shift in power grid demand, the computer reduced the output of Unit 2. This seemingly normal command dropped the massive machine directly back into the highly unstable intermediate power band, the water flow rushing through the penstock instantly destabilized. Chaotic hydraulic vortexes formed underneath the turbine runner, slamming upward against the assembly with immense pulsating force. The microscopic threads of solid metal left inside the fatigue-ruined studs could not absorb this final violent blow. All remaining weakened bolts snapped simultaneously, severing the only mechanical connection keeping the turbine anchored to the concrete foundation. With the fasteners completely destroyed, there was absolutely nothing left to hold back the crushing weight of the river. Nearly 20 bar of highly pressurized water slammed upward against the underside of the steel turbine cover. The unfathomable hydraulic force ripped the entire 920-ton spinning rotor completely out of its housing. The massive rotating steel structure violently tore through the surrounding equipment and launched 3 meters straight up into the air, instantly severing its heavy electrical connections. The immediate physical destruction of the generator floor was absolute. The enormous corrugated steel cover was blown completely out of its seat, flipping over and landing vertically on the floor of the plant. The heavy reinforced concrete foundation surrounding the turbine pit shattered under the extreme stress, firing jagged chunks of stone shrapnel across the room. Essential plant equipment, steel catwalks and control cabinets were pulverized in a fraction of a second. With the spinning rotor ejected from its casing and the heavy seal entirely gone, the main penstock became a wide open pipe pointing directly up into the building. 380 cubic meters of water per second erupted from the ruined empty pit. This uncontained flow blasted a solid, unstoppable pillar of the river directly into the main turbine hull, immediately threatening everything and everyone inside the structure. The explosive geyser of water rocketing out of Unit 2 immediately slammed into the surrounding high-voltage electrical infrastructure. Violent arcs of electricity illuminated the massive turbine hull as the systems short-circuited under the deluge. The plant's total power output collapsed to exactly zero in a matter of seconds. With the main transmission lines severed and local power failing, the entire building was instantly plunged into absolute darkness, leaving only the deafening roar of rushing water. For the maintenance crews and engineers working on the lower levels beneath the generator floor, there was absolutely zero time to react. Freezing river water flooded the subterranean galleries and catwalks at terrifying speed. The furious current battered against metal doors and swept down the narrow corridors. In pitch-black conditions, workers scrambled to find stairwells and exits, but the sheer volume pouring from the open penstock meant the water level rose faster than anyone could climb. Many were trapped deep inside the submerged concrete labyrinth with no possible route of escape. Above them, the catastrophic failure cascaded through the physical structure of the powerhouse. The immense hydraulic pressure and the initial shock wave from the flying 920-ton rotor severely compromised the building's steel framework. Sections of the massive roof above the turbine hull buckled and tore apart. Hundreds of tons of structural steel and metal roofing collapsed downward, violently crashing into the neighbouring machines. Generating units 7 and 9 were directly underneath the falling debris and were completely destroyed by the massive impact. Within just a few chaotic minutes, the destruction was nearly absolute. The relentless floodwaters and falling wreckage took a devastating human toll. 75 workers were killed, either drowned in the rapidly flooding lower levels or crushed by the collapsing roof and flying concrete shrapnel. Of the 10 massive generating units that made up Russia's largest hydroelectric plant, 9 were either severely flooded or entirely annihilated. The station had gone from full operational capacity to total catastrophic failure in the blink of an eye. The total blackout created a terrifying new reality for the survivors. Without electricity, the automated safety systems were completely dead, meaning the massive intake gates at the top of the dam could not close on their own. Unit 2's penstock had become nothing more than an open pipe. The immense pressure of the reservoir was blasting thousands of cubic meters of water per second directly into the shattered turbine hull. This relentless flow was not just flooding the destroyed building, it was actively threatening to undermine the foundation of the concrete structure. A small group of plant workers realized they had to act immediately before the damage spread to the dam itself. They raced up to the crest of the dam, navigating through pitch-black corridors and climbing endless stairwells to reach the absolute highest elevation. At the top, the intake gates were locked in the open position by heavy hydraulic jacks. Because there was zero power to run the motors, the men had to operate the emergency controls entirely by hand. They smashed open the heavy control cabinets and began manually opening the bypass valves, physically bleeding the pressurized oil out of the hydraulic cylinders. Inch by inch, gravity slowly took over. The 150-ton steel emergency gates began to slide down their vertical tracks. The workers had to repeat this exhausting manual process across the intake structures, muscling the valves open in complete darkness while the river continued to roar through the open penstocks beneath them. It took nearly a full hour of desperate back-breaking labour to finally drop the last gate and fully shut off the flow of water into the powerhouse. This heroic manual intervention severed the connection between the towering reservoir and the open generators below. By stopping the deluge, this handful of workers successfully contained the destruction to the turbine hull. Most importantly, they prevented the incredibly powerful currents from eroding the dam's primary structural supports, averting the unimaginable nightmare of a total dam collapse that would have swept away entire populations downstream. In October 2009, the Russian government released the official investigation report. The findings blamed a devastating combination of poor maintenance, actively ignored vibration data, and severely fatigued turbine cover studs. Months of continuous rough running had weakened the thick steel bolts holding the 920-ton assembly down, destroying their structural integrity. Engineers and physicists immediately began debating what actually delivered the final upward strike that severed those compromised bolts. The leading theory points to a hydraulic shock wave known as a water hammer. When Unit 2 was ordered to drop its power output, the automated control system rapidly closed the guide vanes to choke the flow of water into the turbine. This sudden restriction caused a drastic pressure drop, forcing the fast-moving column of water in the draft tube below to physically detach from the bottom of the runner. This separation created an enormous vacuum cavity. When that void inevitably collapsed and thousands of tons of water slammed back up against the spinning turbine, it generated an instantaneous pressure wave. Experts continue to argue over the precise hydraulic mechanics of that final split second. Some investigators suggest an extreme vortex rope or severe cavitation provided the ultimate upward force, rather than a full water column separation. But the specific physics of the breaking point do not change the ultimate conclusion of the root cause. Industrial disasters rarely happen from one clean, unpredictable mechanical break. Unit 2 did not tear itself out of the foundation simply because of a sudden water hammer. It was destroyed because human operators repeatedly forced a structurally crippled machine to run inside an inherently unstable power band. The disaster was entirely preventable, set in motion long before the final hydraulic strike launched the massive rotor through the turbine hall roof. It took years to rebuild Sayano Shushenskaya, eventually restoring its 6,400 megawatt capacity. But the lasting lesson goes beyond engineering. Monitoring equipment is entirely useless if humans lack the authority or willingness to act on the data before a failure becomes visually undeniable. The chilling realization is that this catastrophe did not begin when the 920-ton rotor tore free. It began while the machine was still producing power, quietly sitting one fatigue cycle away from death. Thank you for watching. What are your thoughts on the human element in this disaster? Leave a comment below. If you want to explore more deep dives into catastrophic engineering failures, subscribe to the channel.